Every forest of order n with k components has size n minus k. That's what we'll be proving in today's Wrath of Math lesson. This is a pretty straightforward proof, so I definitely recommend giving it a try yourself before watching the rest of the lesson. Remember that a forest, predictably, is just like a tree, except it doesn't have to be connected. So a forest is just a graph with no cycles, thus its components are trees. That makes sense that trees would make up a forest. So either of these graphs on their own would be a tree, but together they are a forest. And remember that a tree graph with n vertices has size n minus 1. It has n minus 1 edges. I'll leave a link in the description to my lesson proving that result, and we'll be using it in this proof. I'll try to quickly explain why the result is true before we take a look at the proof. Basically, to count the edges in the forest, of course, all we have to do is add up the edges in the different components, which are just trees. The number of edges in each tree is necessarily its number of vertices minus 1. The number of edges in this tree component is its number of vertices, whatever it is, minus 1. Then when we add all the edge counts together for the total, we'll get the number of vertices in the forest, which is n, minus however many components there are in the forest, in this case 2. So our result tells us that since this forest has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices, it should have 11 minus 2, or 9 edges. And we can count them up to verify that count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Look at that. Alright, let's check out the proof. So we'll just say that F is our forest, and it has order n, so it's got n vertices, and it's got k components. So it's a forest that's made up of k trees. Let's call these k tree components of F T1, T2, and so on all the way up through the last component, Tk, where k is greater than or equal to 1. There is at least one component, because if there are no components, then we've got no graph to study. Furthermore, we'll say that n sub I is the order, the number of vertices in the tree component Ti. So n sub 2, for example, is the number of vertices in the component T2. And similarly, we'll say that mi is the size, the number of edges, in the ith component, Ti. Then, how could we rewrite the order of our forest F? Well, the total number of vertices in F has to be the sum of the number of vertices in F's components. So the order of F is equal to the sum of the orders of F's components, all the different trees, which we can write as the sum of ni, where I ranges from 1 up to k. Similarly, if we let the size of our forest be m, then m, the total number of edges in the forest, is of course the sum of the number of edges in its components. So it's equal to the sum of m sub I from I equals 1 to I equals k. That's just adding up the vertices in all of the components, and that's just adding up all of the edges. Now, we want to prove the size of f, this sum here, is equal to n minus k. So how could we rewrite this? Currently, each term in this sum is just the size of one of the components of our forest. In other words, each term is the size of a tree graph. Thus, we could actually rewrite this sum as the sum of ni minus 1 from I equals 1 to k, because the size of each component is just one less than its order. So in general, the size of the ith component is n sub I, its order, minus 1. Then if we wanted to take this really slow, we could rewrite it as two sums that we are very familiar with. First, we would have the sum of ni from I equals 1 to k, so the sum of all the vertices between the tree components. And then add to this the other part of our original sum. So we'll add the sum of negative 1, which is just being done k times. This sum, the sum of all the vertices in the components of f, is certainly equal to n. That's the order of f. And then this sum, the sum of negative 1 k times, what's that equal to? That's equal to negative k. So this is equal to n plus negative k, which of course is equal to n minus k. And that completes the proof. So very straightforward. All we did was recognize that the number of vertices in a graph is equal to the sum of the number of vertices in all of the graph's components. There might be one component, two components, any number. Similarly, its size is equal to the sum of the sizes of its components. Then we just recognized that since F is a forest, by definition, each of its components is a tree. So each component has one less edge than it has vertices, and voila, that gives us our result very quickly. And that is how we prove that a forest of order n with k components has a size of n minus k. It's basically just a generalization of the result that a tree of order n has size n minus 1. Hope this video helped you understand the proof. Let me know in the comments if you have any questions, need anything clarified, or have any other video requests. Thank you very much for watching. I'll see you next time, and be sure to subscribe for the swankiest math lessons on the internet.